So you'll notice by the objective of today's video that the goal is to factor polynomials. And this is an objective that's going to take us a couple of days to get through just because there's so many different ways to go about factoring a polynomial. For those of you who don't know, or maybe you forgot, or maybe you just no one ever told you it exactly, factoring a polynomial refers to the process of taking one polynomial and breaking it up into a multiplication of several polynomials. So the same way we can factor a number, like for example 6 factored is 2 times 3, that's factoring a number. We can factor a polynomial. So we take a big polynomial and we break it into smaller polynomials you can multiply together to get the big one. It's sort of the opposite of the previous objective, right? So in the previous objective, we took polynomials and multiplied them together to get new polynomials. Now we're doing the opposite. We're taking one polynomial and breaking it into 2 or more, right? You'll notice from the title, we're actually going to pick 2 specific methods of factoring to talk about today. GCF, which stands for greatest common factor, and then difference of squares, which is just difference of squares. These 2 are probably the simplest in terms of algorithmically easiest to work your way through. But for whatever reason, they're also very frequently forgotten about, probably because other factoring is requires so much thinking and effort. These are very automatic. People tend to sort of let them slide. So I wanted to give a video specifically to these 2 methods because, like I said, they are often missed. So let's start with GCF, which stands for, like I said, greatest common factor. And like I just mentioned a second ago, it's the easiest factoring method that everyone forgets for some reason. Okay, and probably the best way to think about it is it's just the distributive property in reverse. It's basically taking the distributive property and applying it backwards. Okay, so it's reverse distributive property. And the best way to see it is through an example. So let's just take one right here. So this is a polynomial. It's a cubic binomial with a quadratic term. When I look at these 2 terms, I want to find something that divides into both of them, but I also want the greatest thing that divides into both of them. So the greatest common factor, right? Well, I like to do it numbers and variables separate and then sort of combine them at the end. So the GCF of 10 and 4 is, of course, 2, right? 10 is divisible by 5 as well, but 4 is not divisible by 5. So the greatest factor that goes into both 10 and 4 is 2. The greatest factor that goes into x cubed as well as x squared is x squared, because x squared times 1 gives me x squared times x gives me x cubed. So I can rewrite this polynomial as a bunch of products, right? I can do 2x squared times 5x and 2x squared times 2. Now, if I pull that 2x squared to the front, what I'm left with is 5x minus 2. And hopefully you can kind of see if I had done these lines in this order instead, starting at the bottom and working my way up to the top, that'd just be the distributive property. So I would just take 2x squared times 5x, 2x squared times 2, and then that would be my final answer, right? But remembering in factoring, it's sort of the opposite of simplifying. So I want to start with one polynomial and break it into 2 polynomials. In this case, a binomial and a monomial. Okay, just to do another example, if I have 3 terms, I have to look for the GCF of all 3 terms, right? So looking at just the numbers, 18, 27, and 3, the GCF of those, all 3 of them, is just 3, right? Obviously, these 2 numbers have a GCF of 9, 27, and 18, but the GCF of all 3 is 3. 3 is not divisible by 9. The GCF of the variables is, of course, just x. X times 1 gives me x times x to the 5th gives me x to the 6th, and x times x to the 9th gives me x to the 10th. So the number I'm going to pull out of all of them is 3x, right? And then what I'm left with here, 3x times 6x to the 9th gives me 18x to the 10th. 3x times 9x to the 5th gives me 27x to the 5th. And then 3x times 1 gives me 3x, okay? And then finally, I can sort of pull that 3x to the front. And what I'm left with is 6x to the 9th, 9x to the 5th, and 1. Hopefully you can see if I went up this way, it'd be distributive property. So all I'm doing is sort of reversing the distributive property. Now you don't have to show me all 3 of these lines when you do it. A lot of people can jump just from here to here. Perfectly cool. Okay, but this is the gist of GCF factoring. You just think about the greatest common factor between all the terms in your polynomial, and then you pull it out to the front and consider what's left. Again, it's by far the least work. Maybe difference of squares is less work, but it's one of the less labor-intensive versions of factoring. But people forget it all the time. Okay, so keep an eye out for it. Don't let it slip by. Okay, talking about difference of squares. Okay, so I want you to sort of recall back before we actually talk about using a difference of squares method of factoring. Recall back to what happens when you multiply a square root expression by its conjugate. So we talked about this last week when we were working with square root expressions. Okay, so suppose I have like this, for example. So the square root of 2 minus 4 times the square root of 2 plus 4. And these two are conjugates because, because this is minus and this is plus. Okay. Now, just like I did with polynomials yesterday, I'm actually going to multiply these together on a grid. Okay, and you don't have to do this. You can FOIL it if you want, or you can just do distribution property twice. But I like to do it on a grid like this. So notice I took square root of 2 minus 4, put it at the top. Square root of 2 plus 4, I put it along the side. And now I just multiply rows by column. So root 2 times root 2, of course, gives me just 2. Negative 4 times square root of 2 gives me negative 4 root 2, and then 4 root 2 for these two. And then negative 4 times 4 just gives you negative 16. Okay. Now, the reason why we used conjugates was when we were like rationalizing denominators, it ends up killing the square root because you'll notice I have a 4 root 2 here and then I have a negative 4 root 2 here. So those are actually going to cancel each other out. And all I'll be left with is just 2 and minus 16. And of course, 2 minus 16 is negative 14. So actually, when I multiply these two radical expressions together, the radical piece falls out and all I'm left with is just sort of like a regular old integer in this case. Okay. Well, the same sort of logic is going to apply when I'm thinking about differences of squares. The only thing is instead of a square root, I have x, right? So it's a polynomial instead of a square root expression, but the same pattern kind of holds. If I take x minus 4 and I multiply it by x plus 4, so remember we were doing the square root of 2 before, now we're doing x. Okay, if I do that same sort of grid that I did before, you'll notice I have x times x, which gives me x squared, right? And then negative 4x, and then 4x, and then negative 16. And again, just like what happened with the radicals before, this middle term, this x term, is going to cancel right out. And all I'm left with is x squared and minus 16. Okay, so it almost looks like I just multiplied the first terms and I multiplied the last terms. But what actually happened was these middle terms, this if you're thinking FOIL, this outer and inner, they cancel each other out. And we can see it very clearly over here on the grid. Okay. Generally speaking, this works for anything. So I just picked 4 plus 4 and minus 4 sort of randomly. But generally speaking, I could do it with any two numbers or variables or whatever it is, right? If I take a minus b and I multiply it by a plus b, I'm going to get a squared here and then minus ab and then plus ab and then minus b squared. And this diagonal here is going to cancel, okay? And all I'm going to be left with is the first term squared minus the second term squared, which is what we call, of course, a difference of squares, right? It's something squared minus something squared. And we can always factor a difference of squares into the square root of the first term minus the square root of the second term times the square root of the first term plus the square root of the second term. So generally speaking, these two are the same thing. If I have a squared minus b squared, it's a minus b times a plus b. Okay, we can use this pattern to factor anytime we have a polynomial that looks like something squared minus something squared. That's why we call it a difference of squares. Difference because it's minus, squares because both of these are perfect squares. Okay, so just to sort of take a look at a couple examples. This is an example of a difference of squares. 9x squared is the same as 3x quantity squared, and 25 is the same as 5 squared. So if I want to factor this, I just have to think about what do I multiply by itself to get 9x squared? What do I multiply by itself to get 5? And of course, 3x times 3x gives me my 9x squared, and 5 times 5 gives me my 25. Now notice if you sort of visualize the grid or try to FOIL it, you'll get a 15x term from the outer and a minus 15x term from the inner. Those will cancel out, right? So this right here, written as a product, is the same as this right here. That's difference of squares factoring. And again, it's very simple because it's almost like a pattern that everyone memorizes, but people often forget sort of how to handle it when they see a difference of squares. Now here's another example. And you're probably looking at that going, well, Duhaime, that's not a difference of squares at all because nothing squared gives me 6, at least not nothing rational squared gives me 6, and nothing squared gives me 54. So this is, of course, not a difference of squares, so I can't use difference of squares factoring because otherwise I would have ugly square roots in my factors, and I don't want to deal with that. Well, of course, that would be true if you didn't remember our old friend GCF factoring, right? So I can pull a 6 out of the first term and the last term. Remember how I said it's very easy to forget about GCF factoring? Well, here's a perfect example of what I meant. If I pull a 6 out, well, 6 times x squared gives me 6x squared, and 6 times 9 gives me 54. Now I see x squared minus 9. That is a difference of squares, a very classic difference of squares. Okay, so I can factor that into x minus 3 times x plus 3, because again, that minus 3x from the inner and plus 3x from the outer when I FOIL are actually going to cancel out. So this would be the fully factored form of that. So keep an eye out for those GCFs, like I said way back at the beginning. Okay. Here's sort of an interesting case because I have 81x to the fourth minus 16, and you say, well, that's not a square, that's a fourth. Well, x to the fourth is just x squared squared, right? So when I factor this, I take the square root of the first term, I get 9x squared. The square of the second term is 4, so this actually factors into this, 9x squared minus 4 times 9x squared plus 4. And again, if you think about that 36x squared term you get from the inner and the outer, one's going to be negative, one's going to be positive, they cancel out, okay? We're actually not done factoring this here because if you look at it, this is also a difference of squares, right? 9x squared is 3x squared, and 4 is 2 squared. So I can actually factor this piece again and give me 3x minus 2 and 3x plus 2, and then the 9x squared plus 4 stays the same, okay? So you're probably thinking, all right, so difference of squares, factored it, then I had another difference of squares, factor it. What about this guy down here, this 9x squared plus 4? Is there anything I can do with a sum of squares, okay? And the short answer is no. There's no way you can factor a sum of squares. So 9x squared plus 4 cannot be factored. Okay, you can quickly prove this to yourself sort of just by thinking about the possibilities, right? And one possibility would be, well, what if I did 3x plus 2 times 3x plus 2, right? And of course that wouldn't work because when you do that, you would get the 9x from the first, and then 6x, and then 6x, which would give you 12x plus 4. So 3x plus 2 times 3x plus 2 does not give you 9x squared plus 4. Your only other option was be if I did 3x minus 2 and 3x minus 2, which would still give you the 9x squared and the 4, but again, you're going to have that middle term, that minus 12x. It turns out a sum of squares will never factor, okay? And the reason why a difference of squares does factor and a sum of squares doesn't, just sort of visualize this box here, right? There's no way you can make these two terms cancel without one of them being negative and one of them being positive. Well, if you have one of them negative and one of them positive, you end up with the difference of squares every time. Okay, so these middle term here, this 12x in this case with this AB in this case, it's only going to cancel out if I'm multiplying a negative number or something minus something and something plus something, right? So you need that negative in there, but you can only have one negative in there, and then you automatically end up with a difference of squares. So the short of it is a difference of squares will factor every time. A sum of squares will never factor. So don't even try to do it. There's no way to come up with two polynomials that multiply together to give you this. It just doesn't work out. Okay, so that is it for those two methods of factoring. Like I said, they're probably the easiest, but please don't forget them because they're also very commonly missed, and try to avoid that, like I said, very common mistake.